And it's also on the archive if you wanted to look it up. And it's basically about trying to understand the role of measurement from a control theory point of view. But before I start talking about the result, I think I need to somehow justify my awkward affiliation, although this is probably the conference where I've seen the highest number of Aberystwyth participants or past Aberystwyth visitors. You might not all know where that is and what that is. So I'm trying to put it on the map here a little bit. So this is you. And then if you basically go westwards until you fall into the sea, then you're in Aberystwyth. And the name Aberystwyth decomposes as the Aber, the estuary or the mouth of a river, just like Aberdeen, and Istwyth, which is the name of a river. Now, if you think that this is a rather unfortunate affiliation to have, then you should count yourself happy that I'm not from somewhere above here, which is this place here. But don't worry, don't worry. People find abbreviations, so this place here people lovingly call in short like this. We're a bit more lucky, we call ourselves ABBA, so if you say ABBA, that's fine. Now, if you want to really understand what Aberystwyth is about, you have to look at it by night. You see, this is the Isle of Man here, sticking out in the ocean in the Irish Ocean. And this is Aberystwyth here, sticking out in the what people call the green desert of Wales. So the population density is incredibly low. So this kind of sparkling star here is Aberystwyth. That's how it looks in the daytime on one of the sunny days. On the only sunny day last year. No, just kidding. This is where the university was founded, and actually maybe the single most famous event that happened here was in the basement where they had a cloud chamber in the 1930s, and they found the decay of the muon into something that I don't know. Anyway, it's a beautiful place, and if you haven't been there yet, please come and visit. It's really nice. Check the weather forecast. Now, for the outline of this talk, I can be quite slow because I don't have so much to say, so please also feel free to interrupt me and ask questions and give me your opinions. I somehow have to justify the strange title, so I'm going to speak a bit about Plato's cave, and then I'll talk a bit about measurement and complexity of dynamics, and I want to understand how measurement influences the complexity of dynamics. Then I'll talk about quantum Zeno and something that we introduced which we call Hamiltonian purification. So it's a bit like state purification, but it's also a bit different. And then we bring things together and come to the quantum version of Zeno's cave and draw conclusions. Okay, so what's Plato's cave? I'm sure you all know that much better than me because I only know it from the Wikipedia page. So the idea is that you have some prisoners inside of a cave, and these prisoners will not perceive the world as we perceive it maybe, but they will only perceive a projected world that happens because there's a fireplace here. And then the world that is behind them is basically not visible, and they only see it through their observation. And anyway, I don't know much about philosophy, so that's about what I know about Plato's cave. But the whole point is that what they perceive is quite different from what is behind them. So projections are incredibly powerful, and if you want to see a classical proof of that, go to London, where you can find, for example, this exhibition here by Noble and Webster, who put pieces of junk together, and they design it so that when you project it from the right perspective, you get something that looks completely different. So already in the classical world, projections are quite surprisingly distorting, and so what we're going to do is basically find a quantum version of this. Now, so quantum projections or measurements are, how should I say that? They're much more exciting than the classical measurement, and that's because of the back action that the measurement has on the system. Now I know that some people are not so happy with the term, but let's just call it back action. And they're basically, qualitatively, there are two different effects that we can observe. And one is things like the uncertainty principle, the fact that measurements change the system and do not commute with each other, which is usually considered as something not so good. And then there's also measurement-based quantum computing, which shows that sometimes measurement can have a vast effect and they can do something amazing, namely quantum computing. So sometimes they're very powerful. So what we wanted to ask is what happens generally? I mean, these are specific cases. Somehow in particular, measurement-based quantum computing is a very specific protocol. But how does a measurement generally influence the dynamics of a system? And in particular, we wanted to know how it influences the complexity of dynamics. So, of course, quantifying the complexity of a system or the complexity of a dynamics on a system is not there's not a unique currency or way to do it. But I think in control theory, at least for the unitary case, we have a kind of standard currency there, how to determine the complexity of a dynamics. So if you had, for example, two Hamiltonians and time-dependent constants, and you could design these time-dependent constants so they are controls, and if you want to understand what is then the complexity of the system under your dynamics, under your controls, then what we usually do is calculating Lie algebras. And I think most of you know that by heart, but just to recap the main idea. So you take the Hamiltonians, you decorate them with a complex I, and you then find the smallest real Lie algebra that contains these two Hamiltonians. So in other words, you take commutators and linear combinations and commutators again and so on, and you keep on doing that until you don't get anything new, and then that set forms a Lie algebra. And the reason that the Lie algebra determines the complexity of a system from a control theory point of view is that basically the dimension of the Lie algebra will tell you something about the complexity, and it will also tell you whether or not you can do quantum computation, and more generally, it will tell you what you can do in a system. So if you're not so familiar with that, or if you have any questions, I'm happy to elaborate on that further, maybe at the end, or also now if you want. But I think that's all we need to know from control theory for this talk.
Can I just ask, what is so there's a tilde in quantum computation, but I don't really see how, so what aspect of quantum computation are you connecting to dimension Lie algebra?
Yes, so okay, maybe one equation that I like is that the reachable unitaries of your system are basically given by the exponential of that Lie algebra. Okay, maybe you have to put some kind of topological closure, I don't care, but basically it says what you can do is given by the Lie group that corresponds to your Lie algebra. And if you calculate the dimension, and if the dimension is maximal, you know that you can do all unitaries. And if you can do all unitaries, you know you can do quantum computing. It doesn't tell you, by the way, whether or not you can do it efficiently. That's a completely different question. But any other comments or questions? Okay, so what happens now if we, additionally to these two Hamiltonians, we can also do a projection. So we have, let's say we have a sharp von Neumann measurement described by some projection. How does that increase our capability to do things? And you know, this is a kind of a hard question, because it's a clash of communities in some sense, because the control theorists like to talk about algebras, and they like to talk about differential equations, and the people in quantum information like to talk about operations and CPT maps and those kind of things, and they are working on the integrated level. So mixing these two up, mixing these discrete things up with generators is not so easy, and I think that's why at least in closed loop control, this idea of continuous measurements is so powerful, because it actually allows you to do things with differential equations again. But I wanted to talk about these strong projections here. I didn't want to go into that route of talking about weak measurements. And disappointingly, I don't know the answer. But so what is quite common then to do in control theory is to go and look at a specific limit. So that limit that I'm going to talk about now is a specific case of what you generally can do. And generally, I expect you can do even much more. But the specific limit, at least, I can characterize. Okay, so the specific limit is what people call the quantum Zeno effect. And it is the limit where you do the measurements very, very quickly. So they're still not continuous, but you do them, at time scale delta t, where delta t is really small. So let's see how that works. You're surely familiar with this way of writing the exponential formula. So you might also know that if I make xn dependent, so I take a sequence of xn that converges to x, then that formula is still true. And you probably also know that this also holds for matrices. So that's a really nice theorem. And we can use it to prove the Zeno effect in 2 lines. So what do? We look at projection, time evolution, and projection, and we do that many, many times, n times, where n will be large. And the time evolution will take place on a time t divided by n, so it will take place on a shorter and shorter time as n gets large. So what we can do is the usual trick that we develop the exponent in a Taylor series. And then the only thing that prevents us from rewriting that is that the p is here inside, so we can take that outside because it's a projection, so p squared is equal to p. And if I call this guy here on the top xn, you can see that the first order here was the only one that survives and the rest disappears. So this will converge to p e to the I p h p t p. And that's all there is to know about the Zeno effect. So basically it says that if you're in this very specific limit where you frequently apply measurements, then the Hamiltonian, the original Hamiltonian, is kind of dressed by these projectors on either side. So you get a kind of effective evolution, which is called the Zeno Hamiltonian. And maybe I should point out that this Zeno Hamiltonian takes place inside of a smaller space, which is called the Zeno space. And in the limit where delta t is really small, you never leave that space. So the outcome of the measurement will always be yes. So supposingly you start in the Zeno space. So you start in there, you always measure yes, so kind of the outcome of the measurement is trivial, and you stay there, and inside of that space the evolution is given by PHP. So the advantage of this is that now I can describe the effect of the measurement by a Hamiltonian again. And I know how to deal with Hamiltonians. I don't know how to deal with measurements. So let's see how that works. So what is the complexity of such xenodynamics? So the xenodynamics takes place in a smaller space. So this kind of Zeno space, the projected Hilbert space. Is it simpler? So initially, maybe it's tempting to think that it's always simpler because you're projecting a dynamics into a smaller space, so somehow there's not so much space in there. But of course, the answer is not always, and otherwise this talk would finish right here. So it depends on the rank of the projection, whether or not the dynamics is simpler. And so in particular, if the projection is rank 1, then actually PHP is a trivial dynamics on the Zeno space because it's a rank 1 projection itself, and on the Zeno space it's basically just a phase. So that's what people call Zeno's paradox, right? The fact that you can freeze the quantum dynamics by measuring. So if we go away from Zeno's paradox, we can find examples where actually the complexity of the dynamics is increased. So let me take this example here. This is a 2-qubit example. So we take a projection on a pure state on the first qubit, but we don't actually do anything on the second qubit. So it's a rank 2 projector. So I want to take the state of the qubit here such that it has non-zero overlap with Pauli X and Pauli Z. You can certainly find that state and you can write it down, but I'm just writing it like this. So I take such a projection kind of in some diagonal direction. And now let's see what happens when we apply this projection to two Hamiltonians. So yes.
So you're assuming a sort of von Neumann-Lüders measurement process.
Yes, that's right. Towards the end of the talk, I will come to examples how you can actually implement this without any measurement. In fact, you can implement it with noise as well. It's actually this talk is not so much about measurement at the end of the day, to take that already now. It's more about putting some sort of geometric constraints on your system. So let's look at these two Hamiltonians here. Again, on two qubits, XX and ZZ. So the dimension of the Lie algebra generated by them is 2. And why is that? Because they commute. And they commute because Pauli matrices anti-commute. So if you have the tensor product of two Pauli matrices, they anti-commute twice, so they commute. So if I want to give you a kind of geometric interpretation of what happens here, is that because they commute, it doesn't matter which way around I go. If I first apply XX or ZZ or the other way around, I end up in the same space. So because they commute, the geometry of my space is somehow flat. So now I introduce a projection, and it's exactly the projection from the last slide. So it's the projection that projects in some direction which has non-zero overlap with X and Z. So I do that on the first qubit. So if I do it for the first Hamiltonian, I get P, something proportional to P at least on the first qubit, whereas the second one remains untouched because I only measure the first qubit. So that's my first Zeno Hamiltonian. And if I do the same with the other Hamiltonian, I get PZ2. So PX2 and PZ2 are my Zeno Hamiltonians. Now, of course, you know that X and Z do not commute anymore. So if I take the Lie algebra that is generated by the Zeno Hamiltonians, I will actually get some non-trivial commutators, and I will get a three-dimensional Lie algebra. Now, I just want to emphasize that essentially what I'm doing is through the measurement, I freeze the qubit, the first qubit. So it's really a geometric constraint that I put on the qubit. And the effect of that geometric constraint is that the rest of the system becomes non-commutative. So now we have a three-dimensional Lie algebra, which means that even though we are actually projecting into a smaller space, inside of that smaller space, we've become more complicated, more complex. We can reach more. And so the geometric way of understanding this is that somehow a quantum projection here can introduce curvature into the system. So here it matters actually if I first go in the Z and the X direction or in the X and Z direction. And the difference between these two is exactly given by the commutator. So this is in some sense very different from classical projections and from this from the Plato cave picture, because here actually the projections create some sort of severe distortion to my system. Any comments or questions on this? Okay, so Jake.
So this strikes me as sort of the simplest example of symmetry breaking. And is that going to be a consistent sort of recurring theme here, or is there something?
It is some sort of symmetry breaking, but it's not a usual symmetry as in things commuting with the Hamiltonian, because you cannot understand Lie algebras entirely by symmetries on the Hamiltonian. There's a more general result which explains how you can understand Lie algebras by generalized symmetries on an extended space. So for example, entanglement is not a symmetry, but it's something that is conserved, so there should be some symmetry related to it. And Zoltan Zimboras has a poster on this next week. So in some sense, hand-wavingly, you can think about it as breaking symmetries.
But only in this extended?
Only in some extended space. And the results that explain how that relates to the extended space are actually from last year, so it's not entirely obvious. So the question is then also how general is this effect and how strong is it? So now I want to introduce you to this idea of Hamiltonian purification, which is in some sense much more interesting than what I've talked about so far. But it allows you to prove that this effect is usually very strong and it's usually very general. So forget about everything I've said so far, but at least for the next 2 minutes, and then remember it again. Take two Hamiltonians on some d by d matrix space, some generic Hamiltonians. So they might commute, they might not commute, we don't care. And so I'm going to write down two Hamiltonians on an extended space, which do commute, and which somehow represent these original ones. So I'm taking H1 to be the small h1 tensor identity plus the H2 tensor X. So I extend my space by a single qubit. And I'm taking H2 exactly the other way around. So I take sigma X here, tensor H1, and identity H2. Now these two Hamiltonians commute. And it's easy to see, because if I calculate the commutator, well, if I calculate the commutator between these two terms, they disappear. Because here H1 commutes with H1, and the identity commutes with sigma X, and the same this way here. So the only non-trivial components when I calculate the commutator between these two are the diagonal commutators. So let's look at this diagonal here. I get the identity tensor, the commutator of H1 and H2. So that's this term here. And that diagonal here, I get sigma X squared times the commutator of H2 and H1. And now sigma X squared is the identity, and I have the commutators here just the other way around. So I get 0. So that means if you have two Hamiltonians which do not commute, you can always find some sort of mother Hamiltonian on a larger space that does commute. But of course, that's kind of trivial. I can always take the 0 Hamiltonian as the mother Hamiltonian, and it does commute. So we also need a way to go back again into the original space. And that will be taken care of by this projection here, which just focuses on the top left of the first tensor component here. And so these two terms here will disappear if I project with that. And essentially, under the projection, I get back the original Hamiltonians times some trivial component on the extended space. Okay, so that means that any non-commutative dynamics can be thought about as some kind of simpler dynamics on a larger space. And vice versa, you can go back by performing this kind of Zeno limit. And of course, this is for two Hamiltonians, but you can also do it iteratively to do it for any set of Hamiltonians. So why is this useful in the context of this talk? It's because of a result by Kuranishi from 1952, which I still find very amazing. So let me just tell you a little bit about this. So you know that in three-dimensional space, we can think about any rotation as a rotation around two fixed axes. That's pretty amazing. So you might ask yourself the question, what is, if you go to higher dimensional spaces, how many axes do I need then? And roughly speaking, I mean, it's very hand-wavy, but roughly speaking, you only need two axes no matter how large your space is, because you can always find two generators for any size of the space, such that the Lie algebra that is generated by them is the full one. So somehow this is not a scalable property. So it's very, another way of saying is that almost all Hamiltonians generate the full Lie algebra. So I'm going to take this result for granted for the time being, and I think it's amazing. And so if I apply my purification scheme to this one here, I immediately get the following, that there are some Hamiltonians, namely the purified versions of these guys, which commute such that the projected version of these two will generate everything on the projected space. So that means that there are on a huge space, there are commutative Hamiltonians, such that when you start measuring a single qubit in that huge space, the dynamics on the rest of the system becomes universal for quantum computation. So previously we've seen that for the XX and the YY Hamiltonian, or ZZ Hamiltonian, that we can raise the complexity from a 2-dimensional to a 3-dimensional Lie algebra. But this one here says basically we can go from a 2-dimensional to a D-dimensional algebra, where D is just whatever space we have available. So that is kind of the main result of this talk, which is that projections can raise the dynamics or the complexity of the dynamics by an exponential amount. Now, here comes the most bizarre argument, or the most non-understandable argument in this talk, and I'm happy to elaborate about it. The determinant is a polynomial, and therefore, so hold on a second, therefore, this effect here, which we see for the two specific generators of Kuranishi, actually happens almost always. So that means if we take two random commuting Hamiltonians and we measure one single qubit in that system, then with probability 1, our dynamics will also become universal. So it's not just these very specific Hamiltonians that have that effect, but it's almost all systems which have it. And conversely, because of the purification, any kind of complex dynamics can be thought about in this way. So that's why we call this thing the quantum Plato cave, because somehow I think maybe Plato would have liked it that in the quantum world the projected reality is even somehow more messy in general, and that you can always think of a messy dynamics as something pure and commutative on a larger space. Now, what is this kind of strange argument that the determinant is a polynomial? It's a kind of standard trick in control theory, and I think many of you will be familiar with it, which says that if something is controllable for a specific set of parameters, then it's also controllable for almost all other parameters in the same space. And the reason is that you can rephrase controllability by some kind of rank criterion, and you can rephrase that rank criterion by a determinant being non-zero, and the determinant is a polynomial in some parameters. And if you have a polynomial that is 0, then the 0 set of the polynomial has measure 0. So it's a very standard argument. It's a bit more complicated in this context, but I think it's kind of intuitive.
Can I ask, so it's a universal quantum computer, presumably?
Yes.
And, well, you mentioned that there are issues, well, not necessarily issues, but what about the efficiency?
Yes.
Do you say anything, can you extract anything about that? Is it an efficient?
Let me postpone that to the next slide. I can answer that question. Any other questions or comments? Okay, so actually your question also goes in the direction of how might these look like. Usually I'm not so happy with this argument that random Hamiltonians will generate everything, because in physics we don't find random Hamiltonians. In particular, if you just take a d by d matrices and you create a random one, then you will not find that they consist of two-body interactions, for example. So they will not correspond to anything that you find ever in the lab. So what we find in the lab is not random. So it's then therefore also important to find specific cases of two-body interactions which still work. And so we spend some time on that, but I don't want to spend half an hour calculating boring Lie algebras on the blackboard, so I'm just going to give you one example of such system. So because I like spin chains somehow, I always have to draw at least one spin chain in every of my talks. So here's a spin chain, so spin a half particles on a chain, and these black lines here. Okay, so we've got two Hamiltonians. The red Hamiltonian is XX, just like we had it in the simple example. And the black Hamiltonian is another one. It's mostly a Heisenberg Hamiltonian, so it has couplings XX plus YY plus ZZ between the qubits. And there's this strange term here. I promised you two-body interactions, but actually there's a three-body interaction here. So these kind of interact xxx plus yyyy plus zzz. Yes?
I grabbed the opportunity you mentioned again about this two-body and three-body and body interaction. You said that in the lab we only have two-body interactions, or you were saying that in nature there only exist two-body interactions.
Yes.
Which one of the two? In the lab or in nature?
Well, as far as I understand, in nature there are only two-body interactions. I mean, you can often find effective things which look like three-body terms, and you can play lots of tricks. But if you write down some fundamental law like Coulomb's law, or then you always have only two terms.
Is this a standard argument, or is it like folklore knowledge? It can be proved mathematically?
I don't think it can be proved, but has anyone ever seen it?
You can prove it in the low energy sector of QED. So
With
basically-
assumptions.
No, well, the assumption is that you're working in the low energy sector of quantum electrodynamics. But that essentially means that you're working with a.
Are there any reasons in principle, first principles?
Well, we don't know, for example, in QCD if it's true.
Okay, QCD is a kind of.
In other words, inside of the nucleus, we have no guarantees that this statement is
So I
true,
assume
but,
that you need some assumptions for that.
you just need locality. Actually, you just need Lorentz invariance.
Okay. Okay, so here we have two Hamiltonians, and they commute. Why is that? Well, for the same reason that the other Hamiltonians commuted earlier on, because XX commutes here with the XX component, with the YY component, and with the ZZ component of the black Hamiltonian. And now I introduce some projection that will make this thing universal. So basically, I now measure the first qubit of this guy here in some direction which has non-zero overlap with all three Paulis. I should point out that I had to cheat a little bit, so I also have this kind of constant Z3 term acting here, so that's just adding to the Hamiltonian. And then this projection will freeze this qubit here in a specific state. And the effective system that you then get is basically this one here, where this link here is now the standard Heisenberg interaction. So let me switch back again. So the previous control here is XX, and it just becomes X on the second qubit because you're basically freezing the first qubit. And the many-body term, the three-body term here, when you remove one of the qubit, just becomes XX plus YY plus ZZ. So it becomes the standard Heisenberg interaction. And now this system here is universal. So if you calculated the Lie algebra that is generated by x2 on the end of a spin chain and the rest of the spin chain, you would find that the Lie algebra is actually, to be more specific, is the special unitary one. So it's SU2 to the d minus something, where something is the number of qubits that you have left after taking the projection. So I guess it's n minus 1. Yes?
These x2 and z3, they are the measurement-based type corrections to get back to this graphical. Is that right, or do I misunderstand?
So the x2 comes from the original x1, x2, where we measure the first qubit, so that one becomes a projector. And basically, we are left with something that looks to the second qubit as if we were controlling x2. The Z3 is just an ugly fiddle factor that I had to put in so that the Lie algebra would become the full one. So it might not be obvious to you that the Lie algebra between these two is the full one, but you can kind of do an inductive proof. So it's something.
Are you talking about one-way quantum computation with cluster states?
No, this is not measurement-based quantum. The whole idea was inspired by measurement-based quantum computation because I knew that measurement had power, and I wanted to see how this power translates into something related to control theory.
But this is pretty much cluster state, right?
So this is not a state, this is a Hamiltonian.
Okay.
So it represents coupling. So you have a spin chain, and on that spin chain you start controlling a field on one of the qubits, and then it turns out that the system becomes universal for quantum computation.
So, I mean, that is Heisenberg picture of...
Heisenberg Hamiltonian.
Yeah, Heisenberg picture of cluster state in some sense.
Not exactly, because for the cluster state, I think you only have ZZ interactions, whereas here you have XX plus YY equals ZZ. So it's a bit different. We can talk about it later. Yeah.
Isn't this Hamiltonian easier to realize though in a lab?
Easier?
Yeah, because this only contains two-body interactions.
Oh yeah, sure. We just wanted to have one specific example to see how it works, how it really works. I can write down another example at the blackboard at the end if you want, which does not contain any three-body interaction. So the reason why I have this ugly three-body term here is because it's so simple to show that this works. But you can kind of, maybe I just draw one graph without putting the terms, but you can kind of make another chain which branches out like this. And then you kind of control here and you control here with, so you have H1, H2, and H3. And I need some fiddle factors around here as well to work, but then it works with two-body interactions. It's just harder to present. So the three-bodiness is not essential, and so thanks for actually pointing that out, because it also means that this result from the previous slide, where I said the determinant is a polynomial, so that almost all Hamiltonians have this property. If you find an example with two-body interactions, of course it implies that also almost all two-body Hamiltonians have that property. So the nice thing about this determinant argument is that whatever family you show it for, if you find one example, it holds for almost all examples of the same family. I think there were some other questions, yes?
So you have the Z3 term, which doesn't commute with the previous Hamiltonian, right?
The Z3 term is kind of hardwired in the black one, so it's constant. So we only have two Hamiltonians here, the sum of all the black stuff, and the other Hamiltonian is the red stuff.
Yeah, but the Z3 doesn't commute with H2. Does it violate?
The Z3 is part of H2. It's already fixed inside of H2.
Oh,
so H2 is equal to this plus this. Sorry, I should have explained that better. It's not a separate control, because that would be cheating proper, but it's kind of in there. It makes sure that when you have the X, somehow when the Heisenberg Hamiltonian is kind of the generator of a swap. So one intuitive way of thinking about how this Lie algebra is generated is you switch on the swap and it swaps the X over here. The X, when it's over here, sees the Z and generates a Y. So you have already local control. Now, because the square root of swap is entangling, you have local control plus entangling, so you have all two qubit operations here. But then you do the same thing here and you get the same here, and so you get nearest neighbor to qubit controllability, and then you have quantum computing because you have all nearest neighbor gates. So that's why I need this fiddle factor.
Well, that fiddle factor can be considered as just an on-site magnetic field.
It's an on-site magnetic field, yes. It's not fundamentally problematic, it's just less beautiful. Okay, so now at this point I can also, okay, so these generate the full Lie algebra on the remaining system, except for the phase, which I don't care about. And we have two-body examples. Now I can come back to your question about the efficiency. Actually, we had a good discussion yesterday about that as well. Usually you should not expect this to be efficient, because all the arguments that are used in deriving the Lie criterion include very nasty things like recurrence times and so on. So it can easily take you the lifetime of the universe to actually control such a system. However, for at least some slightly modified version of this spin chain scheme, I can do it with an overhead of n squared. So you want to do computation on a one-dimensional system, you only do it at the end. You have to expect that there's a slowdown by a factor of n at least, because you need to get to the other end and come back. And it turns out that with n squared you can do it. So not all of these are unrealistic. Some of them are realistic. But I don't think of this, the Zeno thing here, I don't think of it as a practical suggestion for doing quantum computing anyway. It's more like trying to understand what the measurement does. Okay, any other comments? Okay, so finally, let's talk about what happens if you're actually not achieving this Zeno limit. So you know the Zeno limit is only one very specific limit in which you're doing things infinitely fast. But what happens if you kind of, what's the second order term when you don't manage to? So I don't have much to say on that, but I want to put a very hand-wavy diagram here. So think about it like this. So think about some measure of complexity here, and think about delta t as the distance between your Zeno measurements. So you'd like to understand how the complexity behaves here. And we know that kind of if delta t is very big, then we're at the case where we don't do any projection. And so the Lie algebra is simple. And on the other hand, if delta t is going to 0, then we know that it's kind of exponentially big. So I would like to understand how is the complexity in between. I know it's a bit hand-wavy. Now we know that if delta t is non-zero, you're no longer constraining yourself to unitary dynamics, because the Zeno limit only becomes a Hamiltonian in the limit. So what is in here is actually that there's a potential, at least, to explore a larger space, namely the space of all CPT operations, or maybe not quite all, but quite a lot of them. And so my conjecture here is actually that the curve should look something like this. My conjecture is that when you go away from the Zeno limit, first you will find that the complexity of your dynamics actually increases further. And that's because you're starting to explore non-unitary dynamics, while the noise is still low enough to have this speed up or have the exponential size. And then as the noise gets stronger, you should somehow get over here. But that's a very hand-wavy picture.
Why do you call it noise?
Pardon?
Why do you call it noise?
Noise, I call it because if you leave the system some finite time between evolution, and you forget about the outcome of the measurement, then you have effectively a CPT map. If you do remember the measurement, then of course you don't have a CPT map, and then it becomes even more complicated. But yeah, it's an important comment. How do I characterize the noise and the complexity in this case? Very good point. So actually, I have some numerical evidence with a big but. So the numerical evidence is what you can just do is you can calculate the second order correction in the Zeno formula, which is quite interesting in itself. And then you can calculate Lie algebras generated by these animals. So you get some Lindbladians in second order, and you calculate the Lie algebra generated by these Lindbladians. And I find that numerically these Lie algebras are bigger, I mean it's kind of to be expected, than the original one. So that gives some evidence. But the problem is, and that's where the but comes in, is that we don't actually have any operational meaning to the Lie algebra generated by some Lindbladians. So in other words, for the control theorists amongst you, the system is accessible, but I don't actually know what the accessibility means physically in my system. If someone knows something about that, I'd be really happy to learn, because I think it's an open question. I think there was some, Madeline, you had a...
But before you were thinking about what happens on the subspace, because you are projecting all the time. So now the evolution happens on the full space, right? Because you have finite time intervals.
Yes.
So is the complexity still in terms of the subspace or the full evolution?
No, you then have the complexity of the full evolution. You forget about the measurement outcome. You have a CPT map, and your dynamics takes place in the two subspaces. If you have a measurement with output 0 and 1, and you kind of have some decoherence between the two subspaces, and you can talk about the directions in the space of this thing that you can explore, and you can find that the Lie algebra is even bigger. So if the Lie algebra, if the previous Lie algebra would be d squared, then maybe this would be d to the 4 or something like that.
So the increasing complexity is also because you actually get out of the space.
Yes, exactly. Not quite d to the 4, by the way, but anyway. Okay. So I don't know how to answer this question, and I think it's an interesting one, but it brings me back to the question of how to describe quantum control of open systems. And I think maybe we'll hear more about this also from Thomas Schulte-Herbruggen in a couple of days. Anyway, so other implementations finally. So we do not need the measurement outcomes in this scheme, because actually even in the Zeno limit we always get 1. So in some sense, what I'm talking about isn't really a measurement. Or it's not a measurement like in measurement-based quantum control, where you quantum computing, where you actually do need the measurement and you need to be adaptive in the future, otherwise you lose all the speed up. So this kind of hints that this can be implemented also in other ways and can be thought of in other ways. And the trivial ones are, for example, a strong amplitude damping channel, which will also fix one qubit in a specific direction if it's really strong. Or some strong fields, which effectively decouple one of the qubits from the rest. So you can think about it in arising in other ways. And so in some sense, the way I'd like to think about this result is that if you put some kind of geometric constraints in quantum mechanics, then generally these raise the complexity of the dynamics exponentially. And it also means that noise can be thought of in this case as the source of computational power. And I think Michael Wolf, for example, has some nice results which are much more wide on that. But this one here says that if you have one very strong amplitude damping noise in your system, then that can be the source of quantum computing. Okay, so that brings me to my conclusions. We've seen somehow that this, also from a control theory perspective, confirms the power of measurement in the quantum world. And in particular, I mean, I think what I'm interested in is characterizing the reachable set given some Hamiltonians and some measurement. And what this result says is that contained in this huge set, at least you have this here, which is the Zeno Lie algebra, and that already can be large. So that's very encouraging. Now to finish with a slightly crackpot equation. So, you know, I like this result, so I just wanted to bring it up here. It's that you know that measurement can also be considered in some models as the source of time. So if you think that the universe itself evolves under a time-independent Hamiltonian with 0 eigenstates, so the universe as a whole doesn't evolve, then you can think of time arising from basically correlations or entanglement by measuring other systems. So now, in some sense, the measurement can explain quite a lot of quantum theory. In some sense, it can explain time. It can explain the dynamical non-commutativity of Hamiltonians through this purification. And I see some people smiling already, so I'm a little bit embarrassed about this conclusion. But anyway, let me just finish that. You know that in some sense, measurement. There are two sources of non-commutativity in quantum mechanics. One is the non-commutativity of measurement, and one is the non-commutativity of Hamiltonians. And so what this means is that the non-commutativity of Hamiltonians can actually be thought of as arising from the measurement. So in some sense, all we have to deal with in order to understand quantum mechanics is the measurement. But of course, we don't know what measurements are, so we are based at the start again. Thank you very much.
Thanks for this nice talk. Questions?
Yeah, something Peter and I were talking about earlier is quantization of fields with constraints. Normally when you quantize a field, you're applying physical constraints. You should only apply the constraint to the Lagrangian or the Hamiltonian and re-quantize. In your case, you're relying on the fact that the projection operation is not a dynamical constraint, it's some other non-dynamical operation. Is that correct?
To be honest, I've never quantized a field in my whole life, so I don't know.
Peter's got a link to the book.
Right.
But it's basically, I worked on quantization against Landau many years ago, and basically to get a consistent description of constraints in quantum theory, you only ever apply the constraints to the Lagrangian. Okay. But that's for dynamical constraints or physical constraints rather than projections.
I can't even say let's talk about it in the coffee break because I don't know what a Lagrangian is either. But I'd like to learn a bit about it. But I don't think we can manage in the coffee break unless it's very long.
Do it over lunch.
But I mean the fact that geometric constraints introduce complexity shouldn't surprise. Also already in classical dynamics you have that. But the point is that here it does so in a drastic way in some sense.
The point in field theory is that if you add an additional constraint into a physical system, it actually changes the commutation relation.
Okay. Yeah, that sounds very similar.
I mean, you worry only about complexity, but sometimes it's, for example, good to know what energy do I use over my control. Do you have some way how to characterize how much resources this projection is taking?
No, I don't. I mean, definitely, if you want to do things infinitely fast, it usually takes infinite energy. So I'm worried that it might not make it look very good if I did count the resources.
I had a comment about, so it's about this constraint, I think, question, right? So it's actually, there is this recent experiment by Aberystwyth and also another one with where they, Paris, where they actually are they try to do this same kind of quantum dynamics instead of using projection by some kind of Hamiltonian dynamics. So which is just essentially, for example, their case is just that you have a harmonic oscillator and you want to essentially limit the dynamics to a finite dimensional part of this thing. So in order, instead of doing some measurement which essentially locks the dynamics to n levels, to n first levels, what they do is essentially they couple it to a qubit or to another nonlinear system, and they apply some field which is just detuning, detunes, let's say the nth level from so the transition from nth level to the n plus first level. So it's just the Hamiltonian kind of dynamics which puts some constraint on your Hilbert space, and which does it effectively the same thing as xenodynamics. So I would say that this is possible to do it.
I mean, this is what I kind of in two words just put here with the strong fields. And actually my co-authors Saverio Pascazio and Paolo Facchi are, I think, involved in that work.
This may have been implicit on your comment on noise, I'm not sure, but often what happens if you try to do a projective measurement in the lab is it doesn't happen with probability 1. So with some finite probability, say 90%, you project it, but with 10%, nothing happens at all. So have you considered where the transition would be with that level of coarse graining from neglecting all measurement results to neglecting, say, just 10% of them, which is what typically happens when you try to do these things in the lab?
I mean, my feeling is that we'll come back to this curve here where you're effectively going from delta t going to 0 to some finite one. So I think in general you should still expect that the complexity increases.
But now instead of delta t,
there will be some probability, yes.
And we need to know where that peak is.
Yes, but I mean this is a very, very hand wavy curve, and it's very hard because I'm after some exponential complexity. Even doing things numerically doesn't work because I can only.
It does go up initially.
Yes, it does go up initially. Yes.
More questions?
Maybe comment. You mentioned Paolo Facchi. They wrote a nice paper with Daniel Vidar where they tried to go through all the cases that give you the xenodynamics and this effective Hamiltonian. And of course, it's amplitude damping that gets you that, but also this dynamical decoupling, adding noise, any adiabatic elimination. It all gives you always this Hamiltonian. Yes. So I think most practical quantum computing schemes they are using exactly this kind of Hamiltonian.
Right.
Or this Q-bus quantum computing, which is a big buzzword. You couple many qubits to one common mode, and then you do measurements on that common mode, then effectively again you get this Hamiltonian.
I see.
There are really tons of examples.
Okay, nice. Yeah, I should also.
There's no general framework for it probably, but I think Paolo Facchi and Saverio Pascazio, they were maybe the closest ones trying to
characterize all of them. I should also mention that John Goff has recently put something on the archive about xenophiability in the SLH formalism, so there's also some kind of framework that allows you to do similar effects there.
So I guess as a sort of a comment and a question, I find in the end this fundamentally confusing because on the one hand it suggests that complexity is the natural outcome of any scenario. And on the other hand, we have essentially classical behavior, which we can simulate reasonably efficiently. I mean, still can be NP hard, but compared to the underlying Hilbert space, it's not. And so I'm just trying to understand a little bit where the difference is.
Right. I'm not entirely sure if I understand your comment correctly, but I think one thing that you know, when I talk about this purification, that any non-commutative dynamics can be thought of as some kind of classical commuting one in a larger space, I'm not suggesting that this is a way of calculating things in a more simple way on that larger space, because the problem is that you can't just purify, calculate there, and then project. It's only under the Zeno projection that you get back, which means that the Zeno dynamics does not commute somehow with calculating things in the larger space. And I think that resolves maybe the confusion about what is simpler and what is harder, because it's two different procedures.
Let me say it slightly differently. If I think about the emergence of classicality as essentially sort of weak measurements, decoherent things, then one would naturally assume that the corresponding subsystems would be extremely complex, based on the arguments here, because they're being sort of constantly monitored and measured. That seems to be counter to the
Right. Okay. So maybe I'm not sure. I'm still not sure if I understand it. But let me then answer a different question, which is that maybe you're thinking about this point here, where I mean this raise of complexity through noise only happens for very, very strong noise, in the limit of infinitely strong noise, which in the real world probably doesn't exist. So there you have a raise, but if you're actually closer to this point, then you have a loss of complexity through noise.
Okay, so maybe we continue the discussions over lunch. Let's thank Daniel again.
Thank you.